Hi everyone, I'm Alankrita Bhatt and I'm going to present some work with my advisor Young-Han Kim on sequential prediction under log laws with side information. So let's start with describing the setting. We're considering the case where the data is stochastic, which means that we consider two random variables x and y, which are jointly distributed. And I'm going to describe the joint distribution of x and y in this slide. Right, so denoting the marginal of x by px, the conditional PMF of y, which is binary, given x is characterized by some f that belongs to this larger class calligraphic f. So each element of this class describes the relationship between y and x in terms of a conditional distribution, pf y given x. And in this work, we will be considering a specific form of the class calligraphic f, which is described as follows. So each f is described by three things: theta 0, theta 1, and g. Theta 0 and theta 1 are two numbers in 0 to 1, and g is a binary function that's defined on calligraphic x. The g belongs to a larger class of binary functions, and this larger class is assumed to have a finite VC dimension, which we will denote by d. Then y given x is distributed as a Bernoulli random variable with p equals theta gx, which means that y is either Bernoulli theta 0 or Bernoulli theta 1, but which one depends on x through the value of the function gx. So let's take a simple example here. If we choose the class of functions g to be the class of all one-dimensional thresholds, right? So the function gx is 0 for everything less than some threshold a and 1 for everything greater than the threshold a. This is a classical example of a class of binary functions with VC dimension equals 1. So let's say we choose the particular gx to be the threshold function with threshold at half, right? Then y given x equals 0.1 is distributed as Bernoulli theta 0, and y given x equals anything greater than half, like 0.8, is distributed as Bernoulli theta 1. Right, so we are studying the online learning problem, and the setting is online learning with stochastic data with distribution as described in the previous slide. So online learning can be interpreted as a game between learner and nature. So nature picks a specific conditional distribution f from the class of conditional distributions and a certain distribution of x px. Neither of these are known to the learner. So for example, continuing the example of the 1D threshold class from last slide, let's say nature chose this particular f and chose px to be uniform 0, 1. Right? So we'll use this as a running example through this slide to illustrate the game. So at time step I, the side information xi is generated according to the distribution px. So let's say x equals 0.3 was drawn. Then both the learner and nature have to assign a PMF to yi, which is equivalent to saying that they have to choose a probability that yi equals 1. So for example, let's say that the learner determines that on the basis of the history so far, a yi will be 1 with probability 0.25. Nature, on the other hand, knows the exact conditional distribution yi given xi, since it knows f, and it just assigns that as the PMF. So in our example, given side information 0.3, y is 1 with probability 0.1. So that's what nature is going to assign, right? Next, yi will be drawn as Bernoulli theta gx, which is Bernoulli 0.1 in our case, in this example. And let's say yi equals 0 was drawn, okay? Then both the learner and nature incur a loss of minus log of the probability they assigned. So if they assign a very low probability to yi being 0 and yi turns out to actually be 0, as it did in our example, they will incur a very high loss. So we can see that in our example, nature assigned a higher probability to yi being 0 and correspondingly incurs a lower loss than the learner. Right, so we can now define the exact problem that we're studying, which was first formulated by Fogel and Feder in 2017. So, as the game continues, the losses of both the learner and the adversary will accumulate over time, and we have the regret, which is the expected value of the cumulative loss of the learner minus the expected value of the cumulative loss of nature. And the expectation is with respect to the random x1 through n and y1 through n. Subsequently, we can also define the min-max regret, which is the minimum value of the worst case regret. And the questions that we're interested in are, first of all, a characterization of Rn. Specifically, how does it vary with n and the dimension d? Secondly, what is the min-max optimal probability assignment Q or any other probability assignment Q that achieves near to the min-max regret or even a vanishing sublinear regret, right? So in this work, we give some partial answers to these questions, amongst others, a lower bound on Rn and a probability assignment Q star that achieves sublinear regret. And I'll talk more about these results in detail towards the end of the presentation, including a comparison to the existing work. So there are a few reasons why we're interested in studying this problem. First of all, the log loss is a very standard loss in information theory that has much significance operationally in problems such as compression. And this survey of Merhav and Feder provides several detailed arguments justifying the use of the log loss. Moreover, log loss also turns up in other problems such as online density estimation with the KL divergence. Right. So let's now look at some related work. So first of all, if there's no side information, then the problem just reduces to the problem of universal compression of an IID binary source. So Yn is distributed IID according to some Bernoulli data, and we have this expression for the min-max regret, also known as the redundancy in this case. So all of the xi's are removed, and this can be seen to be the KL divergence between the actual distribution of Yn p theta and the assigned distribution of Yn q. And this expression has been characterized quite sharply as half log n plus some lower order terms. And the min-max redundancy is actually achieved by a mixture probability assignment Q, which can be thought of as a Bayesian mixture over all possible p thetas with the Jeffreys prior, which in this case turns out to be the beta half-half prior. And all probability assignments that we construct in the paper are based on this idea of using a mixture probability assignment with some proper prior over the class F. So another line of very closely related work is that studying online learning problems through the lens of sequential complexities, which are the sequential analogs of concepts such as uniform convergence and Rademacher complexity. So these ideas apply to the current problem, provide an upper bound of order d log n on Rn non-constructively, which means that these bounds are proven without actually constructing any probability assignment. So they proceed via using min-max duality and analyzing the dual thing. Right. So we can now talk about some of the main results in the paper. So firstly, we construct a probability assignment Q star that achieves order square root dn log n prepared. And we also provide a high probability version of this above bound, right? So building on the mixture probability assignments from universal compression that were mentioned earlier, our upper bound is achieved by a probability assignment that's based on a mixture over the class of conditional distributions F. So roughly speaking, we're taking some sort of a Bayesian mixture over the class F with some carefully chosen prior W, and then building upon this to construct a probability assignment that ends up achieving this upper bound. So Fogel and Feder, who introduced and first studied this problem in their work, They also did propose the idea of using such a Bayesian mixture, but in their mean result, they ended up constructing a probability assignment based on the idea of a branching mixture method, which seems to be quite different from the one that mentioned here that we ended up using. And their method achieved also a square root and log n regret. Right. So, however, both of these assignments are clearly suboptimal and off by a square root n factor, considering the upper bound that was achieved by using the sequential complexities method, which tells us that the Rn is at most order d log n. So there must be a probability assignment that achieves that regret. So we also provide a d plus log n lower bound, which together with the sequential complexities upper bound shows that log n is the right scaling of Rn for this problem. Also, now since we know log n regret is optimal, then there must be a probability assignment that achieves it. So we tried to constructively achieve it in some simpler special cases, and we were able to do so for the following. So when the class of functions is finite, this class has VC dimension at most log g, and we were able to achieve log n regret for this case. When G is the class of half spaces, d-dimensional half spaces, this class is known to have VC dimension d. And when Px is uniform over the unit sphere, we used a mixture probability assignment to achieve order d log n regret. Similarly, when G is the class of axis-aligned rectangles in d dimensions, again, this class has VC dimension d, and Px is uniform over the unit cube, we were able to achieve d log n regret. And if we modify the problem to make it a little simpler, such as when xn, the site information, is available non-causally, which means non-sequentially, so all at once rather than sequentially, or when Px is known to the learner, we can also achieve order d log n regret. So let me conclude by summarizing the remaining problems. So there's still several remaining problems, such as, first of all, constructing an optimal probability assignment for the VC class, for which we know regret attains regret growing as d log n. So this is still left. And constructing a probability assignment with optimal or even sublinear regret for any arbitrary class f of conditional distributions, rather than just the special VC class that we have considered in this paper. So that's all. Thanks a lot for listening.